Yes, so today I'm going to talk about products from macroalgae biomass and particularly about high value markets and seaweed biorefinery, looking at the whole concept from biomass to production to products. So, what are the specific topics in this presentation? Quick introduction again into what a cascade biorefinery, a seaweed biorefinery is, talking about some markets and products, biofuels, which include, it's an umbrella term for bioethanol, biogas, biodiesel, and so on. I will pick some of the biomaterials that are relevant for the different seaweed types and also add some high value chemicals and high value markets, although I already have to say the borders here are a bit fluid, but I will explain this in more detail and talk about how to evaluate the market and think about production costs, sales price, and so on, getting the bigger picture of everything. So, what is a seaweed biorefinery, or what is a blue biorefinery? So, first, biorefineries integrated facilities valorizing aquatic biomass, in our case, macroalgae, and converting them into multiple products and emphasizing the circular economy aspects and approaching zero waste. And particular in the case for seaweed biorefineries, why is seaweed a good candidate for a biorefinery? It has a high potential due to abundance of the raw material. It's underexploited worldwide, no doubt about that. It has a lot of high value components, and particularly the side streams are currently underutilized. So if we think about conventional seaweed industry, how does it usually work? They target conventional factory. They might target one main component of the seaweed. So for brown seaweed, it would be alginate. For red seaweed, it would be agar or carrageenan. For green seaweed, it would be ulva, and they extract this one main polysaccharide, which is 10 to 30% of the dry matter, and the other 30% are thrown away. They are basically wasted. They go back to the ocean or are dumped in other ways. And another point is why they usually can't utilize them in addition is that the traditional processes to extract these polysaccharides often contain toxic chemicals like formaldehyde or other organic solvents. That you don't want to find in your product if you want to use the side stream as animal feed or for pharmaceutical or medical products. In seaweed biorefinery, the approach is different. There is the concept of a cascade extraction. So you would like to extract in order an array of different high value components, and you would like to utilize all the side stream, and the side streams should be directly integrated in your factory. And basically it should be processed all in parallel. And you would also like to avoid, or you are going to avoid toxic chemicals to not spoil the side streams and approach zero waste. You, of course, never totally get zero, but you try to go as close as possible. And you also in the biorefinery, and this is actually one of the toughest aspects. You want to balance all the purification effort with product yield and market values, and this is actually a pretty complex task because you have to adjust machine size and so on. You have to think about how much material goes into which stream, and your entire factory is has to be to some extent flexible, but you want to lay out your factory in a way that it can handle different amounts of material. So how, as I just explained, how would the conventional seaweed industry look like? You basically start with the seaweed, then first there would come a wash step. The exact chemical process is, of course, different for each type of seaweed, but you can really summarize it in a way that you start with a wash that is usually neutral or acidic conditions. Then you start your extraction process, which is often neutral or alkaline and uses higher temperature. And then at this step, you divide your seaweed into the liquid fraction, which should contain your main product, the polysaccharide that you're targeting, and all the rest, the other solid side stream, goes to waste. And indifferent or different to that is the biorefinery approach, where you try to utilize the side streams. So, for example, the wash step that I just mentioned is, if you think about it, basically already an extraction too of other materials. So you have like a crude seaweed extract that in itself could be a product. It can be used in agriculture industry as biostimulant or biopesticide on the field. It can also go to cosmetic industry. You can further purify this crude extract and end up with, yeah, purified high value components such as laminarine, fucoidin, or pigments. And a similar approach can be done with the on the bottom part here with the solid residue. So the crude residue uh, in itself can also be a product because you extracted polysaccharides. This crude residue will often be enriched in proteins. So it could theoretically be, with minor washing steps, already a protein rich feed, animal feed product. It can be used as fertilizer or soil conditioner because it tends to bind water and still contains a lot of valuable components, or as in the iCulture project, which is, yeah, the base of this summer school here now. We look into fermentation of this solid side stream. So you would hydrolyze the side stream first, basically break down the residue into other monosaccharides or oligosaccharides, and let bacteria convert this biomass into other high value components. This is not the, I would say, not the most common use, but this is what we target in this project, for example. Um, so what are the global seaweed markets? What is the raw material that is available? So worldwide, there are currently roughly 36 million tons or megatons harvested, and the majority of that is comes from Asia, and in Asia it is cultivated. So it's largely China and Indonesia who have these gigantic seaweed farms, and they are responsible for the main part of all the harvested seaweed. In total, you can see that red and brown seaweed are by far the dominant species there, or for or groups of seaweed for the industry, with both roughly 18 million tons. And green seaweed for industry basically plays no real role. Um, and yeah, but that's a worldwide picture. The majority is cultivated. In Europe, it looks a bit different. In Europe, the majority is wild harvested, with only a minor fraction of cultivated seaweed. So seaweed farms is, yeah, 600 to 3,000 tons here annually, and the seaweed farms are mostly along the Atlantic coastline in Norway, France, partially Ireland, Scotland, Faroe Islands. And but much bigger amount is harvested from wild seaweed, 200 to 300,000 tons. And this is only 0.1 to 0.2% of the seaweed biomass along the coastline. And as I mentioned before, it's also a fast regrowing resource. So the potential to increase the industry here is actually very big. Um, Coming to the first, let's say, product category, biofuels, just the principle, very short, biofuels umbrella term. Biogas, you would take organic material, uh, basically put it in a silo, close the lid, have the right bacteria, and they start anaerobic bacteria, and they start to digest the biomass and produce methane. Bioethanol, it's roughly the same, but you would use a hydrolysis or hydrolyzation step before. This can be enzymatic, acidic, or thermal to convert the biomass into also monosaccharides or oligosaccharides. And then instead of bacteria, you usually use yeasts for fermentation, and they produce ethanol. And biodiesel basically plays no role too for seaweeds, because biodiesel is based on the lipid fraction of the organic material, and seaweed has very low amounts of fat. But in general, you would theoretically you would take the organic material, you would extract the oil or the lipid phase through presses or organic solvents or both, and then you would perform a transfer esterification, splitting the fatty acids from the glycerine, and then the liquid fatty acid fraction would be the biodiesel or bio oil. Um, why would you use why would you even think about using macroalgae for biofuel? One reason is, as I said, very little lipids. So you have like mostly carbohydrates, which could be fermented or digested to methane. You have no lignin in macroalgae. Why is this relevant? So in terrestrial plants, lignin has the function, for example, of making the wood stronger, but also because it kind of sterically hinders bacteria and fungi, and has also minor antibacterial properties. But it's more the steric effect that it is hard to access the material, the cellulose or carbohydrates from plants that have a lot of lignin for the bacteria. So the digestion is generally low. Seaweed are fast regrowing, and they are a third generation feedstock, meaning they are not competing with the food production of terrestrial plants. What is the disadvantage? Of course, as I mentioned before, if you use the entire seaweed, it has a lot of high value components, and you transform high value components like alginate or carrageenan or fucoidan into low value products like ethanol or methane. Um, Yes, but how is this potentially still an option? Yes, of course, if you take the cascade approach and don't use the entire seaweed biomass, but rather use a side stream. So what would be best here in the biorefinery approach? It would be transforming the solid residue into biofuels. What are other biomaterials? So the main polysaccharides in each of the seaweeds. Red seaweeds, they are mostly built of agar and carrageenan, which are galactan-based polysaccharides. Brown seaweed are made of alginate, and green seaweeds are made of ulvan, which is rhamnose and xylose largely, or xylan, which is a polysaccharide of xylose. And yeah, so basically all polysaccharides, all made of sugars, and almost all seaweed polysaccharides are to some extent charged. So they have sulfate groups or carboxylic acid groups, which is different from cellulose. Uh, Talking about alginate in particular, alginate is built of manuronic acid and glyuronic acid, M and G units. I will not talk too much about the chemistry, but for a basic understanding, those are the two units of alginate, and the ratio and also block structure, but mostly the ratio of these two sugar units defines the properties of an alginate. So if your alginate is better as a viscosifier or for the formation of gels and films is kind of determined here. And this is because the G blocks here, I think you can see my cursor. Um, Let me switch to this. This is maybe better. Yes. The G blocks here are able to bind calcium, and this forms a gel. Or this creates the possibility of form networks. So when you have like many alginate chains in the solution, you form junction zones with calcium between these long polysaccharides, and this creates a scaffold, a network of alginate chains. And this is basically the yeah, the most commonly used form in food industry and medical industry, science in general, to how to gel alginate. You can use other divalent cations, but calcium is the most commonly used. Um, just briefly, what is an hydrogel? Hydrogel is a network of cross-linked hydrophilic polymer chains. So you interlink all these chains, and they bind a lot of water in them. You basically here you look at an alginate gel cylinder, and the properties of the alginate cylinders are basically defined by the dynamic moduli. It's in short, you would just to say it very simple, you would squeeze or turn or twist these gels, and then you would look, do they deform, do they break, are they brittle, are they elastic, do they bounce back? You look at these properties, and this is yeah, determined by many aspects, but mostly the m&g unit of the alginate. And these hydrogels, of course, this gives them a lot of use applications in the food industry, but also those hydrogels, they can mimic soft biological tissue like skin, organs, muscles, and so on, or for the cells. If you put in cells, 3D printing, cell cultures, the cells will feel as if they are in a natural environment. So where else is alginate used? As I mentioned, it's largely used in the food industry as a thickener and stabilizer for yogurt and dairy drinks. It also is used in almost any ice cream that you eat. It gives some additional smoothness, and it prevents ice crystals from forming. It is used for coating or film formation on sausage skin. So traditionally, sausages were placed into washed columns, and most small butchers still do it that way. But industrial production of sausage skin is often done by alginate. So in the top left picture, you see the meat coming out of an extruder and then going into an alginate bath. And there you often have alternating alginate calcium baths, which forms the gel around the meat. And then the sausage is hanged up for drying, and you have perfectly fine sausages. Also, they are used. Alginate is also used for dental implants as at the dentist when they make these, yeah, copies of your teeth. They are used in drug delivery systems or capsules for pills, and a big utilization is also pharmaceutical industry as an anti-reflux agent. So what does the when you have heartburn? So what does the alginate do? It absorbs excess stomach acid, basically buffers it a bit, but also creates a film on top of your stomach that prevents excess acid to yeah, be pressed up your throat again. Um, very similar agar from red seaweed. A difference between alginate and agar, for example, is that it doesn't require an additional crosslinker. The agar forms hydrogels through thermal reaction. So the natural state of the agar is basically being in a double helix at room temperature. But if you heat up the agar enough, 80 to 100 degrees, this double helix unwraps. The agar polysaccharide chains happily float around in the solution, bounce left and right. And if you then cool down the solution again, they will basically grab the first other strain that they string that they find and start to form double helixes again. And then it basically depends on the concentration of the agar in solution, the molecular weight. Also partially how fast you cool, how strong the gels that you form with agar are. And this has many applications in the food industry, of course. It's also very convenient if you're able to process a food and can determine these properties by heating and cooling your product. Or can regulate these, not determine, regulate these properties. So it's used in jellies, puddings, desserts, candy, meat in the pet food industry, and of course, if you're biologist who has worked with cell cultures, it's very likely that you worked with agar plates in the past. Um, Coming to bioplastics. So what is generally the problem with plastics? Roughly 400 million tons of petroleum-based plastics are produced annually, and those mostly end up in landfills and unfortunately also the ocean. And degradation roughly takes 200 to 1,000 years, with a lot of follow-up problems, harming wildlife, creating these microplastics, and potential health risks like endocrine disruptors that also impact potentially our hormonal balance, hormonal shifts, and this potentially has consequences that we can't even foresee by now. And how is this then done with current solutions with traditional bioplastics? They often use cornstarch, which or cellulose, but particularly cornstarch is has the advantage that it competes with food production on land. And why potentially bioplastics from macroalgae? So agar and alginate, they can produce strong, flexible, and transparent films, which is fantastic for many applications where you want to replace plastic, and you can modify the properties of these films with other components from the seaweed. So if you blend into specific amounts cellulose, ulvan, carrageenan, chordin, mannitol, you can regulate elasticity, hardness, and create properties that are superior to current paper or cellulose-based bioplastics, and they are all biodegradable and even edible without any issues. Problem with bioplastics from macroalgae, if we talk about bioplastics from these purified materials like agar or alginate, these bioplastics would be very expensive compared to conventional plastic, plastic in particular. And all components are from seaweed are at least partially hydrophilic. That creates problems if the product that you want to cover with it is a wet product. It will slowly dissolve or make the alginate or agar plastic wet. It can, yeah, just soften it too much, rot or other problems. And it's also not particularly suitable if the product, for example, is stored in a wet environment. Um, it also has, in general, inferior mechanical problems compared to conventional plastic, but there the problem is more not so much that you can't create the same hardness or flexibility and so on, but that it is impossible to um, achieve all properties that a general plastic has with these bioplastics. So if you want to make your plastic harder, you will probably lose transparency or other consequences. So to some extent, we have to admit that plastic itself is a pretty impressive product. Although we don't like it in our environment, it is very versatile, and it is very hard to mimic all properties that plastic has at the same time with bioplastics. But what are potential solutions? Instead of, we could use the entire seaweed or side streams of the seaweed as composite materials instead of purified components. Here on the side on the picture, you can see some products that prototype products that we made that Alginor made in the algae film project. The little plate on the bottom is from seaweed residue, and the paper wrapping for the fries is also made from seaweed. So this reduces the costs dramatically if you take side streams instead of the purified components. You can also use plasticizers. Of course, you would then always want to use food-approved plasticizers. Glycerol, for example, is. But yeah, you have to add other components to the seaweed to reach the mechanical properties that you want. To improve the water resistance, one of the best solutions is coating. I think this is, if I would say, what should future research projects focus for seaweed bioplastic? I think in the past, the possibilities with the what the seaweed, the alginate, and so on can do is pretty much mapped. Now, I think a big way where these products could improve in the future is finding the right coating that yeah gives the alginate or seaweed bioplastics additional desired properties. Um, and another way how the bioplastics are currently already used is not to make entire bioplastics, but have these combined plastics. It's also called biofilled conventional plastics, where 10 to 50% of biopolymers are added to the base plastic, and those are usually then combined in the final production step, which is also often thermoforming or some high shear, high temperature extrusion process. So your polyethylene or whatever is blended with some dried pulp, cellulose, seaweed residue, and so on. And what effect does it give? It basically, the resulting plastic has almost the same mechanical properties as the regular plastic would have, but the inclusion of these polysaccharides creates tears later and little brittles and fractions in the plastic when it later is on the dumping field and so on, and bacteria and water, frost, and so on can break down the plastic much faster. So instead of centuries, we talk about decades. It's still not fast, but it actually is a lot better than the plain plastic. And I think what is the most important when you want to a solution for bioplastics or with bioplastics, you just have to target the right application. So as shown here in the picture, if your material is not water resistant for a long time, then think about single-use plastics. Also, currently, paper straws that kind of nobody really likes, they can be improved a lot with inclusion of alginate or seaweed material, which gives them hardness very similar to plastic. Also, since seaweed and biopolymers, they are fully biocompatible and non-toxic. Wound dressings, stents in the body, all these medical applications, uh, they 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 are a very good candidate to be used there. So how does that look if we come back to this biorefinery conventional seaweed industry approach? Where would those materials, these bioplastics, fit in? We could either think of low value, high quantity. This is these bioplastics for single use from seaweed residues. Or if we talk about the purified alginate, purified agar, and so on, those would be for high value, low quantity bioplastics, where it's important, where you really want a biomaterial, but you want it to be transparent or something. So that those are the things you have to later consider. What is the market size? What can my product do? Talking about pigments, so all of the mentioned seaweed clads, they have of course all pigments, and they have to all extent value to different degrees. So important pigments from wet seaweed are phycoerythrin and phycocyanin. Not so important to talk about everyone what they do, but they are of course bioactive. They are also used as food coloring agent and in cosmetic industry. In brown seaweed, I think this is here in the list the most important one. There is the fucosantine, and that's the dominant carotenoid in the brown seaweed, and it has high commercial value because it's actually one of the few components that is in clinical trials and so on proven to affect the fat metabolism in the body. So it kind of shifts your fat metabolism, that your body burns fat faster and switches from carbohydrates to particularly fat. And it's even used in medical treatments to treat people with fat liver disease, or like a clinically ill liver that accumulates fat. And yeah, there is a large market for both pharmaceutical products but also food supplements in fucosantine. Green seaweed, to be honest, basically has nothing. Of course, it has pigments, but it's chlorophyll A and B and beta carotenoids, which you find in basically any plant. So it's not really worth targeting these components from green seaweed. But if you, for example, from brown seaweed, if you extract fucosantine, you would do this with organic solvents. And there you would co-extract also chlorophyll and potentially to minor extent other beta carotenoids. But fucosantine is a beta carotenoid, and yeah, you would basically potentially separate chlorophyll and fucosantine, but not fucosantine and other carotenoids. Um, but this is, as said, an organic solvent extraction, and this is a bit tricky to combine with the general approach of the seaweed biorefinery for two reasons. First, you as I use organic solvents. Of course, there are green organic solvents, but then there is the question: how do you treat the residue of this? At which point do you take it? And the sheer quantities. You those are basically specialized products that can likely be produced better from microalgae because they are in there in higher quantities, and you would use smaller fractions of your raw material if you integrate fucosantin extraction in your biorefinery. You would just take 1%, 2% of your harvest to go into this production line, but you would not make this fully integrated. The entire side stream of this goes into fucosantin. That there would be a mismatch of the hundreds of tons of raw material that you collect versus how much would even fit in a Soxhlet extraction system. Um, Yes. Talking about proteins, as mentioned earlier, it's also not very relevant for seaweed directly in terms of isolating proteins, but the residue, the side stream, is a potential good target. Why is it hard to isolate the proteins from seaweed? This has been tried now for decades, and it has a couple of issues. So first of all, the protein content in seaweed is not so high. It is a bit higher in green seaweed, but green seaweed is not harvested in an industrial scale. If we look at red and brown seaweed, particularly brown seaweed, the protein content is very low. And the other problem is that the polysaccharides in the seaweed, both in red and in brown seaweed, they solubilize and precipitate and so on again at pretty similar conditions. So an extract and a pH value where you would extract the protein, you would also extract the polysaccharides. If you want to precipitate it with, again, at a different pH or with ethanol, the polysaccharides also precipitate. And additionally, the polysaccharides are strong viscosifiers. So the moment you get the protein in solution, the solution is so thick that it's like really hard to even filter or perform any other tasks with it. So alternatively, what can you do? You can enrich the protein content, basically, as mentioned before, by extracting the polysaccharide. So when if you extract the main polysaccharide, you often have a protein residue in your cellulose or whatever is left fraction. And this is then a potential candidate after some minor washing, for example, for animal feed. There is also big interest in peptides from seaweed. There is a large fraction of yet unknown peptides that have potential antimicrobial and bioactive properties. But to be honest, to be fair, those are, I would say, at this stage, totally on a research level. There is no extraction protocol, there is no target market, no product, and so on. It is very likely that we will find something there, but at the moment, industrially, it's not relevant. Um, so where would these protein enriched products fit in here? They would also be in this solid residue, and this would depend on, as before, what are the previous washing and extraction conditions that determines what is left in your residue, and then you can think about, does it make more sense to turn this into bioplastic? Does it make more sense to turn this into protein-enriched feed material? Does it make more sense to ferment it? Fucoiden. Now we're going to these other high-value components. Fucoiden, very briefly, structure is a polysaccharide based on fucose. It has a highly complex structure. It is branched, sulfated, it has different sugar units, and it is known to have a large range of bioactive properties. And these bioactive properties, they are mostly dependent on the molecular weight and the degree of sulfation. And the just one second, I think here, yes. Um, and the applications you will find used in cosmetics for its moisturizing and anti-aging properties, in personal care. It's in toothpaste in Japan on the market for its antibacterial properties. There are anti-herpes creams with containing fucoiden for its antiviral properties, and there are other medical applications. For example, it's used in horse surgery because it has an anti wound adhesion effect. So it prevents scar formation in when surgery is performed in different tissues. So yeah, and as mentioned before, I made here basically a rough draft. Here you see molecular weight distribution, and you can think of different molecular weights of fucoiden are used for different products. So for creams and so on, you would often go for the lower molecular weight options. For yeah, anti inflammatory. There is a eye disease. You can later check that out. It's called age-related macular degeneration, or surgeries. You would use more in the middle field of molecular weight of the fucoiden, or for tissue engineering, 3D printing, and so on. You would usually prefer the fucoiden to be as large as possible to stay in the matrix. Um, and there are many potential pharmaceutical applications that are currently under research and development. So we really have a growing market here due to the anti-inflammatory, anticoagulant, anti-cancer, and so on properties. And this is like very important to consider when constructing a biorefinery, because the purified fucoiden, we talk just about 100 tons worldwide. That's basically the market size. But those are sold for a high price, roughly 250 to $1,000 per kilogram. But of course, depending on the molecular properties and the purity, it can also be sold for a lot more. Crude fucoiden, which is often used for food supplements, often just dried seaweed extracts, or sometimes even just dried seaweed, is sold for much less. But yeah, can be used for cosmetics or, as I said, food supplements. And there is another very important product, which is seaweed extracts in the agricultural industry for biofertilizers, biopesticides, and those are sold for just $3 to $10 per kilogram. But the total market size is gigantic. It's 60,000 to 80,000 tons, and the production is actually very simple because you can skip a lot of the purification that you would otherwise do with the purified fucoiden. So here we can look at this biorefinery and market value approach again. So here we would think with fucoiden and seaweed extracts coming from this liquid side stream. And here you could think of, yeah, this is a low value product, but high quantities and a lot less work for purification. Or you go the route for further purification and aim for high value products with lower quantity. Cosmetics is kind of both, so I put it in brackets there. You find cosmetics on both sides, but this is something you always have to balance or calculate. If you approach like biorefinery and get ever involved in this, you will calculate this back and forth a million times, which approach is better, because oh yeah, I will come to this because this is it's not only market size and product volume, but it also very dependent on which machines you buy. Do you buy a dryer for the Fukoiden here when you produce 1 ton, or do you need a dryer for producing 50 tons? Or the same for the seaweed extract, and this will very much change the outline of your factory. So if you build a factory, what considerations do you have to do? You, of course, as mentioned, just with the Fukoiden, you look at market size and production capacity, and you have to think about how flexible is your factory to changing markets. Is your factory adaptable? This, of course, adds costs to the construction of the factory, but it gives you a lot of additional security because you can, with the same raw material, you can target different markets, and you can take into account market developments in the future. So as I said, Fukoiden, for example, has a lot of potential future applications that are currently under development and under research. So now you might decide, okay, I just do the seaweed extract, and 1% of what I extract here goes to Fukoiden production, and the rest goes to agriculture. But in the future, with a growing market for cosmetic and pharmaceutical products for Fukoiden, I might put 2% or 10% of the seaweed extract into Fukoiden production. And you also have to think about production costs versus product price. And there, one of the major factors is purification. Purification adds a lot of different filters, water evaporation system, heat costs, and so on. Very often, couple percentage in more purity might add tremendous amount of extra costs. So you might settle for we just go for 80% instead of 90 or 95, and production will cost half. um, yes. Additionally, you have to think about the technology readiness level. This is basically my last point, and then I'm done. Technology readiness level of your uh, product or the production. I mentioned before the biogas production and the iCulture approach that we have with this project. And of course, iCulture targets high value products, which are tremendously superior and then have like a lot higher prices than just putting your biomass, converting it into methane. But on the other hand, especially if you deal with large amounts of raw material, tons of side streams, what are you going to do? Do you have to wait for an AI-controlled precision fermentation with engineered bacterial strains that will produce, where you target 10, 100 kilogram, and so on for now, or where the whole setup will be ready in 5 years or 10 years or whatever? Or are you going to just dump it into a big tank and make methane out of it? Basically have almost no profit, but you can utilize all the side streams right away. So time aspect there is very important. If you just think about value, the iCulture approach is a lot better, of course, than producing bioethanol or biogas. But as an intermediate solution, it might be a lot more reasonable to first go for biogas. Yes, and market readiness level, similar thought, but more towards the product. You might have created a superior product in the lab, but you have to think about, okay, does this already have all the regulatory approvals? Do I have a customer for this? Are there other customers on the market outside who know a product already and where you could sell it to as something similar or as something better to an existing product? So there is this overall scale. You look at technology readiness level and market readiness level, and you divide these into different steps of, okay, I thought about the product, I tried it the first time in the lab, now I make 10 grams in the lab, I pilot it, and so on. And also the market. Is there something existing on the market yet? Do I have a customer, a company who will just add my alginate to their ice cream and my alginate is better, so they will prefer it? Or is this something the market has never heard of before? And all of these things you have to consider when you build the biorefinery, when you divide your seaweed into the different components and when you target different products. So yes, that's basically what I said, what I wanted to repeat. So you look at all aspects of the biorefinery, how much side stream, 10%, 90% main product goes into each category, how far is the market and process developed. Will I flood the market with too much of my product? Should I divide it in several? Should I ferment the majority? Should I just make bio plastics out of it, soil conditioner, and so on? And for all these components, you have to find also the right machine size, quantities, tanks, reactor sizes, and so on. So it is a lot more expensive to create running biorefinery, but the potential reward is also a lot higher, and you have a setup that is a lot more resilient to changing market demands and changing product demands. And that's it. Thank you.
Thank you very much, Dr. Georg, for the insightful topic. So, if you have any question, you might use the chat to ask anything. I already see some questions in the chat.
Should I pick some, or will I think
Yeah,
you or Theo Harris or everyone is.
you, you
Um,
can pick.
yes, okay. I will check. What is the lowest? Uh, yeah. What is the lowest cost way to degrade a cellular chain? I'm sorry, I'm not sure what is meant with that. Um, Yeah, how fast can bioplastics be degraded? That really depends on the bioplastic. So, for example, if you make an alginate bioplastic, they are, for example, also already in the market. You know these from your dishwasher, these dishwasher pads. Tabs that are often in this biodegradable foil. I think it's most commonly it's alginate or cellulose, and they dissolve in water right away. So you basically have the full spectrum of, if you throw it in water, it dissolves, or you can even put it in your garden under earth, and it might take weeks, similar to paper. Or it's integrated with other plastics, and then you reduce the time from 1,000 years to 100 years if you make these combined materials. So that really depends on your product. So, but you would like to make the product, keep the shelf life as long as possible in the store, but you want to have it degraded as fast as possible after the store. And it's always a trade-off. It's always a trade-off, but you basically have the full spectrum available. Um, yes, I think that answered the question. What are major determining factors? I think I answered that. Does it tend to be more difficult to get regulatory approval for products produced through more complex cascade processes? I would say no. That is fairly similar. You This largely depends on the raw material you use, and you have these. You can divide your factory also into sections, so you can have a factory that produces something food grade for the food grade market. So these are the approvals you need. But you can, for example, have a side stream coming from that. And if you kind of separate this side stream from the main process lines and you do an additional conversion in some form, you dry it, you do like a precipitation or something, this precipitated intermediate can be considered as a new starting material. And then for the next approval, you can just get the approval of this starting material to the new final product. So of course you need more regulatory approvals because you have more products, but the regular approvals in general are not harder to get. Um, yes. Okay, there is the question if it's technologically mature. That really depends on, on the product. I would say yes, but some no. So, yeah. Uh, if if there are more questions, I think I answered. Oh, what is the main bottleneck in scaling seaweed by refinery, and which fraction of biomass is currently the most valuable in terms of improving multi-product valorization? So, that of course depends on the type of seaweed. I can best talk about brown seaweed because that is what we have in our factory, and we do a physical separation of different seaweed parts. So the brown seaweed looks a bit like a palm tree, and we separate the stipe and the leaf fraction as a first step in our biorefinery, and I mean, it depends uh, a bit then again how your layout of the total biorefinery is, but I would roughly say the stipe is more valuable because the alginate, which is the main product still, in the stipe is more valuable than in the leaf. The stipe alginate has higher G content, but it really this really depends on both the type of seaweed you're using and which products you're aiming for. There is no general answer.
Yeah. Thank you very much for
So perfect,
answering.
Georg. It's a nice response, and thank you very much for the offer during your holidays. And I'll try. It's very nice connection to my presentation, very relevant to you, and I will try to see the systemic approach. And we hope that it helps, especially the young researchers. Yes. And
Fantastic.
it's something very important to our participants. It's not very often industry to be and present this kind of approach. Usually, most industries keep secrets. They don't say too much, and so this is another reason to thank Georg for the participation. Thank you again.
Thank you. My pleasure.